Right, so today we are dealing with the heat equation in 3D, which is the natural physical setting, or actually in any dimension. So this is the space dimension. So the heat equation has been studied a lot, and it writes as U T. So T is again the derivative with respect to time equals the Laplacian, which is you take the second derivative, for example, uxx plus uyy plus uzz, etc. for all the space variables. You have an initial condition, and you have that u is 0 at the boundary. So this is known as the Dirichlet boundary condition. All right, now what we want to prove is that actually the Laplacian verifies the conditions of the Hale-Yoshida theorem, and then it generates a semigroup, and so the semigroup satisfies this differential equation. People have worked a lot on that, and they have worked on different Banach spaces, right? So we are going to discuss a little bit those different settings. So the first setting is the H minus 1 setting. So what is the H minus 1? So the H minus 1 is the dual space. So I remind that the dual space is the space of the Néel linear functional with values, continuous with values on R, defined on a Banach space. And here the Banach space is H10. So here, the first setting that we could do is to take X as H minus 1. So now your Laplacian is so now, so the domain of the Laplacian is H10. And when you do that, you can prove that A generate a C0 semigroup of contractions on X. So I don't give the detail, but as we done before, you need to prove that lambda A minus A is 1 to 1. So what we need to do is you take lambda I minus A, apply to some U equals F. And so actually, so to solve this equation, it actually comes from the representation theorem. And then you need to get the estimate. So we are not going to do these things. One reference, which is one of the main references that I have been using for the course, is the book of Havre, and this is done in the example 4.1.1. All right. Much more known setting for students is the L2 setting. So in this case, we will choose X. X equals L2. Again, the domain of A is H1 0, and we want to prove that in this case, so the operator A, when we choose x to be L2, the domain of A is H1 0. It's an exercise that you can do, is to prove that A generates C0 semigroup of contractions. So we are going to do this one in quite detail. Those are some things that you should know. All right, so we want to prove that that A generates a C0 semigroup of contractions. So to do that, first, dA is dense in L2. Those are classical results from the Sobolev space theory. Next, we want to prove two things. So first, that minus A plus lambda identity is a projection from dA onto L2, and then to complete the proof, we need to prove the estimate on the operator norm of the resolvent. So to do that, in fact, it relies on things that you did in your first master year. So let's consider any f in L2. You need to prove that this has a unique solution in H1 0. Okay, and so to do that, a classical thing is to name this AU of V. So in the sense of distribution, this equation rewrites actually as AUV equals the integral of FV. So we can just adopt that. So now, if we can prove that A of UV is a bilinear continuous form and coercive on H1 0, with H1 0 endowed with the classical norm on H1, and if FV is a linear continuous form on H1 0, then we're done. We know that there's exists a unique solution of 3.8. And that's the case. So next, to prove the estimate, actually you only need to, okay, the right hand side is not correct here. All right, so next we need to obtain this estimate for any positive lambda. So we just proved that there exists a unique U such that integral of grad u grad v plus lambda u v equals fv. So if I choose v equals u, you obtain that square plus lambda into u square equals f u. All right, so what I obtain that here the lambda norm u L2 square is less than FL2 times u L2. This is Cauchy-Schwarz. Okay, so I'm done because now if I divide by the norm of u in L2, I obtain lambda norm u L2 is less than norm of f. But u is exactly, so it's lambda identity minus a minus 1 f is less than f. All right, so this gives exactly what I want, because this means that the norm of this operator is less than 1 divided by lambda. All right, so the L2 case is works very well. It requires only techniques from your graduate studies, and you can solve this problem. So there is some needs to go to LP. And okay, the theory works for LP, but it's more technical. So we can prove that. So for p between 1 and plus infinity, you can adapt also for p equals 1. But here we just talk about p is more than 1 and is less than infinity. So your space X is LP. So of course your operator is the Laplacian, and the domain of A is now instead of H10, since you work at LP, you replace it by W10, and you take the intersection with W2P because you want to define the Laplacian. Okay, then you can prove that A generates a C0 semigroup of contraction on X. Classical books are Vrabi and Paisi. All right, so that being said, we will do some things as an exercise. So first, D of A is dense in LP. This is a classical result in Sobolev space. Next, you need to do the same thing. So you pick up F in LP, and you need to prove that there exists a unique solution in LP of that. This is technical. All right. So this will take a very long. That's not the focus of the course. However, it's interesting to get a glimpse of that. So we will spend the next lecture on things related to this problem. Okay, but right now, we just refer to this is the very classical book of Gildberg and Schrödinger. So it gives you for any f in LP, there exists a unique u in d of a, such that this equation is satisfied. Okay, so what we are going to do now is to obtain again this estimate here, but in the LP case. All right, so we just want to replace 2 by P. Let's think about that. Okay, so let's do that. So I will assume that U is positive. It's just to avoid some technical. So you can see that you can do it if U is whatever. Okay, it's just to avoid some just some computations. Okay. All right. So we have minus Laplacian U plus lambda U equals F. So F belongs to LP. P is more than well, we will work with the different terms here. So let's start with Laplace, the lambda U. So if I multiply lambda U by, so it's U here P minus 1, because I assume that U is positive, so I just simplified that. And I integrate, I just get the lambda integral UP, which is lambda norm of U in LP to the power P. Okay, so if you multiply that by the norm of U in LP times 2 minus P, you will get the same here. And here. So you get exactly the norm of U LP square. Good. Okay, now let's work with this one. So integral of F, and I multiply that by U P minus 1, and you don't forget here, no, U 2 minus P and LP. Okay, let's do first that, and at the end we will multiply by that. So here, what I will do, I will do the Young inequality. So here I have that F U P minus 1 is less, at the end of the day, I want the norm of LP. So let's do that. The norm of F in LP times the integral of U P minus 1 Q to the power 1 divided by Q, where 1 divided by P plus 1 divided by Q equals 1. All right, so this is good because I want that. Now let's work on this one. So, so first, PQ, so I get PQ minus Q. This is, so since you have that PQ equals Q plus P. Right, from that, you multiply both sides by PQ, you get that PQ equals Q plus P. So PQ minus Q is P. All right, so this is good also, because here, what I get here is exactly, so it's the norm of U, this is the norm of U in LP to the power P divided by Q. Okay, but now we have this term. So I have norm of U in LP times to the power 2 minus P times U LP P divided by Q. All right, but so again, P divided by Q. So let's do that. P divided by Q, so multiplying this one by P gives 1 plus P divided by Q equals P. So P divided by Q is just P minus 1. So at the end of the day, I got U LP 2 minus P times U LP and P minus 1. So this is good because now 2 minus P plus P minus 1 is just U LP. So finally, by doing these computations, what I get is that integral U2 minus P times F U P minus 1. So assuming U is positive, but if not, you just do with the other expression and it works as well. I find that is less than norm of F in LP times norm of U in LP. All right, so the last term that I need to consider is what is minus Laplacian U times U P minus 1. So if I do that, I apply the green inequality. So this is integral grad U P minus 1. So, you know, if I just derive that with one of the variables, let's xi. So U P minus 1 xi is P minus 1 U P minus 2 UXI. All right, so I will do here, this is the, so this will be the integral of, so P minus 1 U P minus 2 And here I got the norm of the gradient, so the square. Okay, but since here u is positive, this is positive. So what do I get at the end? I get exactly that lambda norm ULP square is less than FLP times ULP. So it gives me that lambda, so it gives me that ULP is less than 1 divided by lambda FLP, which is exactly the norm of lambda identity minus A minus 1F in LP less than 1 divided by lambda.